Nearly 5 decades into its mission, Voyager 1 has begun transmitting scrambled data from interstellar space that has left NASA scientists completely baffled. The spacecraft, now positioned over 25 billion kilometers from Earth in 2025, recently started sending corrupted signals from its flight data subsystem that take 22 hours and 35 minutes to reach mission control. These mysterious transmissions represent the first time in 48 years that Voyager's instrument data has been so severely garbled, with the spacecraft's attitude control system reporting impossible readings while somehow maintaining perfect communication with Earth. What could be causing this unprecedented malfunction in a probe that has operated flawlessly for nearly half a century? The answer lies in understanding how this remarkable mission began, the genesis of humanity's greatest journey. In the mid-1970s, NASA engineers faced an extraordinary challenge that would push the boundaries of spacecraft design. They needed to build a probe capable of surviving a journey to the outer planets using technology that seemed primitive even by the standards of the day. Computer systems were basic, power sources unreliable over vast distances, and no spacecraft ever operated for more than a few years in deep space's harsh environment. The engineering team at the Jet Propulsion Laboratory had to create systems that could withstand temperature swings from 400 degrees Fahrenheit to minus 300 degrees Fahrenheit, survive cosmic radiation bombardment, and maintain precise pointing accuracy across billions of miles. The spacecraft's entire command memory would fit in under 70 kilobytes, less than a simple smartphone app today. Every component required redundant backup systems because repair missions were impossible once the probe left Earth orbit. NASA's ambitious plans centered on seizing a once-in-176-year opportunity. Astronomers had calculated that the outer planets would align in such a way that a spacecraft could slingshot past Jupiter, Saturn, Uranus, and Neptune on a single ride. This rare celestial arrangement would allow the probe to use each planet's gravity as a natural accelerator, dramatically reducing fuel requirements and travel time between targets. Without this alignment, separate missions to each planet would have taken decades and required massive rockets that didn't exist. The spacecraft that emerged from these design challenges weighed 1,592 pounds and stood 13 feet tall, roughly the size of a small car, including its extended antenna and scientific instruments. Engineers equipped it with a radioisotope thermoelectric generator that would convert heat from decaying plutonium into electricity, providing a steady power source that could theoretically operate for decades. The probe carried 11 scientific instruments designed to study magnetic fields, plasma particles, cosmic rays, and photograph planetary systems. Mission planners originally scheduled Voyager 1 for a primary mission lasting 4 years, with possible extended operations for another year or two if the spacecraft remained functional. The probe was designed to complete flybys of Jupiter and Saturn, photograph their moons, and gather scientific data before its systems would inevitably fail. Engineers built in some margin for extended operations, but they never seriously considered that the spacecraft might still be transmitting data in the 21st century. The launch window opened in August 1977, and NASA had only weeks to get both spacecraft into space before the planetary alignment would no longer support their planned trajectory. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th, 1977. Despite launching second, Voyager 1 followed a faster trajectory that would allow it to reach Jupiter and Saturn ahead of its twin. The launch vehicles were Titan III rockets, among the most powerful available at the time. As Voyager 1 began its journey toward Jupiter, mission controllers started realizing they had built something far more durable than anticipated. The spacecraft's systems continued functioning flawlessly month after month. Its instruments remained calibrated, and its communication systems maintained clear contact with Earth across ever-increasing distances. The probe's nuclear power source performed better than predicted, and its computer systems showed no signs of degradation from prolonged cosmic radiation exposure. The transition from a temporary planetary exploration mission to humanity's longest-running space adventure happened gradually as Voyager 1 exceeded every performance milestone. What began as a 4-year mission to photograph Jupiter and Saturn evolved into an unprecedented journey toward interstellar space. Engineers started planning extended mission phases they had never seriously considered during the design process. By the 1980s, it became clear that Voyager 1 would continue operating long after completing its primary objectives. The spacecraft's trajectory was carrying it toward the edge of the solar system at 38,000 miles per hour, faster than any human-made object had ever traveled. Mission planners began envisioning scenarios where the probe might actually leave the solar system entirely and begin transmitting data from interstellar space. The spacecraft's remarkable longevity created new challenges its designers had never anticipated. Communication delays grew from minutes to hours as Voyager 1 traveled farther from Earth, making real-time control impossible. Ground controllers had to develop new procedures for managing a spacecraft that operated almost entirely autonomously, with commands taking over 20 hours to reach the probe and responses taking another 20 hours to return. As Voyager 1 approached its 48th year of operation in 2025, the gap between its original mission timeline and current reality had become almost surreal. A spacecraft designed to last 4 years was still transmitting scientific data from beyond the solar system, operating with 1970s technology in conditions its creators had never imagined. The probe's computer systems, memory storage, and scientific instruments were functioning in an environment where no Earth-based testing could have predicted their performance. The engineering success of Voyager 1's extended lifetime has made its recent signal anomalies even more puzzling for NASA scientists. After nearly 5 decades of reliable operation, the spacecraft that exceeded every expectation was about to embark on the most spectacular phase of its journey, racing toward encounters that would rewrite our understanding of the outer solar system. Racing through the outer solar system. Voyager 1 accelerated toward Jupiter at a velocity that stunned mission controllers who had calculated its trajectory months in advance. The spacecraft crossed the asteroid belt between Mars and Jupiter in early 1978, becoming the first human-made object to navigate this treacherous region of space debris and rocky fragments. Controllers at the Jet Propulsion Laboratory watched their screens as telemetry data confirmed the probe had survived the passage unscathed, its instruments still functioning perfectly despite traveling through an area where impacts from asteroids could have destroyed the mission instantly. The spacecraft transmitted its first images of Jupiter in April 1978 when it was still 160 million miles away from the giant planet. These early photographs revealed atmospheric details that ground-based telescopes had never captured, showing swirling storm systems and cloud patterns that extended far beyond what astronomers had predicted. As Voyager 1 approached Jupiter throughout 1979, culminating in its closest encounter on March 5, 1979, its cameras and scientific instruments began collecting data that contradicted decades of theoretical models about the planet's composition and behavior. The most shocking discovery came from Jupiter's moon system, particularly Io, which appeared in Voyager 1's cameras as a world covered with active volcanoes, contradicting every scientific prediction that small moons should be geologically dead. The spacecraft captured images of volcanic plumes shooting sulfur dioxide 190 miles above Io's surface, proving that tidal heating from Jupiter's massive gravitational pull was keeping the moon's interior molten and active. Scientists had expected to find a cold, cratered world similar to Earth's moon, but instead discovered the most volcanically active body in the solar system. The gravitational slingshot maneuver around Jupiter accelerated Voyager 1 to speeds that exceeded its original design specifications by thousands of miles per hour. The spacecraft used Jupiter's immense gravitational field as a natural accelerator, gaining velocity that would have required massive amounts of fuel to achieve through rocket propulsion alone. This technique allowed the probe to reach Saturn in just over a year instead of the multiple years that a direct trajectory would have required. Saturn's encounter. On November 12, 1980, revealed the ringed planet's atmosphere contained approximately 7% helium compared to Jupiter's 11% composition, while the ring system surrounding Saturn displayed intricate structures that ground-based telescopes had never resolved. Voyager 1's cameras revealed thousands of individual ringlets separated by gaps and divisions that created a complexity far beyond the simple ring system that astronomers had observed from Earth. The spacecraft discovered shepherd moons that gravitationally confined ring particles within specific orbital zones, explaining how Saturn maintained such well-defined ring boundaries over millions of years. Titan emerged as Saturn's most intriguing moon when Voyager 1's instruments penetrated the thick atmospheric haze that obscured the surface from view, detecting a dense nitrogen atmosphere with traces of methane and other organic compounds that created conditions where liquid hydrocarbons might pool in lakes and rivers across the moon's landscape. The Titan flyby trajectory required Voyager 1 to pass beneath Saturn's south pole, which permanently altered the spacecraft's path and ended its planetary exploration phase. This maneuver sent the probe out of the ecliptic plane contains most planetary orbits, directing it toward interstellar space at an angle that would carry it away from any future planetary encounters. Mission planners had designed this trajectory knowing it would sacrifice additional planetary science for the opportunity to study Titan's unique atmosphere. Communication systems maintained constant contact with Earth throughout these planetary encounters, despite distances that stretched across hundreds of millions of miles. The spacecraft's 12-foot diameter antenna transmitted data using frequencies of 2.3 gigahertz and 8.4 gigahertz, while ground controllers sent commands at 2.1 gigahertz through the Deep Space Network's massive radio dishes. Signal travel times increased from minutes to hours as Voyager 1 moved farther from Earth, creating operational challenges that required mission controllers to plan activities days in advance. Each planetary encounter pushed Voyager 1 deeper into uncharted regions of the solar system where no spacecraft had ever operated. The probe's trajectory was carrying it toward the outer boundary of the solar system at a velocity of 38,000 miles per hour, faster than any human-made object had ever traveled. Mission scientists began to realize that Voyager 1 might actually cross into interstellar space within a few decades, transforming a planetary exploration mission into humanity's first probe of the space between stars. The technological achievements demonstrated during these planetary flybys established Voyager 1 as the most successful deep space mission in history. The spacecraft's ability to maintain precise pointing accuracy while traveling at tremendous speeds allowed it to capture detailed images and scientific measurements that revolutionized planetary science. As the probe continued racing outward from Saturn, mission controllers tracked its progress toward regions of space where no human technology had ever ventured, wondering what discoveries awaited in the vast emptiness beyond the solar system's edge, breaking the ultimate barrier. By August 2012, Voyager 1 had traveled farther from Earth than any human-made object in history, but scientists still weren't certain whether the spacecraft had actually crossed the boundary that separates our solar system from interstellar space. The probe was operating in a region where solar wind particles from our sun collided with cosmic radiation from distant stars, creating a turbulent zone that made it difficult to determine exactly when the transition occurred. Mission controllers knew the spacecraft was approaching this critical threshold, but the boundary itself remained invisible to most of the probe's instruments. The heliopause represents the point where the solar wind from our sun loses its influence and gives way to the interstellar medium that fills the space between stars. Scientists had theoretical models about what this boundary should look like, but no spacecraft had ever approached it before to provide actual measurements. Voyager 1's instruments detected changes in the cosmic ray environment and solar wind behavior throughout 2011 and early 2012. But these changes were gradual rather than the dramatic shift that many researchers had expected. The definitive proof came from an unexpected source when Voyager 1's plasma wave instruments detected oscillations caused by a powerful solar eruption that had occurred months earlier. The spacecraft's plasma wave instrument measured the frequency of electron vibrations in the surrounding space, which revealed the density of charged particles in the immediate area. These measurements indicated that Voyager 1 was surrounded by a much denser plasma environment than anything detected within the solar system's protective bubble. Scientists analyzed the plasma wave data and calculated that the electron density around Voyager 1 was approximately 80 times higher than measurements taken just outside the heliopause boundary. This dramatic increase in particle density provided conclusive evidence that the spacecraft had entered a fundamentally different region of space where the influence of our sun's solar wind had been replaced by the interstellar medium. The plasma wave instrument had effectively become Voyager 1's compass for navigating the transition between solar and interstellar space. The official crossing date was determined to be August 25, 2012, when Voyager 1 was positioned 121 astronomical units from the Sun, equivalent to approximately 11.2 billion miles from Earth. At this distance, sunlight required 16.89 hours to reach the spacecraft, and radio signals took the same amount of time to travel between Voyager 1 and mission control on Earth. The probe was traveling at a velocity of 17.043 kilometers per second relative to the Sun, fast enough to cover the distance from New York to Los Angeles in under 4 minutes. The magnetic field measurements during the boundary crossing surprised scientists because they expected a dramatic change in field direction when Voyager 1 entered interstellar space. Instead, the magnetic field changed direction by only 2 degrees, indicating that the local interstellar magnetic field was aligned almost parallel to the solar magnetic field in that region. This unexpected finding revealed gaps in the scientific community's understanding of the heliopause boundary. Cosmic radiation levels increased dramatically after Voyager 1 crossed into interstellar space, with high-energy particles becoming approximately 100 times more abundant than measurements taken within the heliosphere. These cosmic rays originated from distant stars and galactic events, creating a radiation environment that was far more intense than anything the spacecraft had encountered during its journey through the solar system. The increased radiation levels posed potential risks to Voyager 1's electronic systems, which had been designed in the 1970s without consideration for such extreme conditions. The interstellar medium revealed itself to be a complex environment filled with gas and dust particles that had been expelled by dying stars throughout the galaxy's history. Voyager 1's instruments detected hydrogen atoms, helium particles, and heavier elements that formed a tenuous but measurable substance between stellar systems. The temperature of this interstellar material was surprisingly cold, measuring approximately 15,000 degrees Celsius, which was much cooler than the million-degree temperature of the solar wind that dominated space within the heliosphere. Communication delays continued to increase as Voyager 1 traveled deeper into interstellar space, reaching over 17 hours each way by the time the boundary crossing was confirmed. These extended delays meant that real-time control of the spacecraft became impossible, requiring mission controllers to plan operations days in advance and rely on Voyager 1's autonomous systems to handle any unexpected situations. The spacecraft had to operate independently for extended periods while commands and status updates crawled across the vast distances at the speed of light. The instruments aboard Voyager 1 had to adapt to measuring phenomena that their designers had never anticipated when the spacecraft was built in the 1970s. The cosmic ray detector, which was originally intended to study radiation near Jupiter and Saturn, became the primary tool for monitoring the interstellar radiation environment. The magnetometer, designed to measure planetary magnetic fields, now tracked the subtle variations in the interstellar magnetic field that pervades the space between stars. The transition into interstellar space fundamentally changed Voyager 1's mission from planetary exploration to galactic astronomy. Instead of studying individual worlds within our solar system, the spacecraft became humanity's first direct probe of the interstellar medium that connects our sun to the rest of the Milky Way galaxy. Scientists realized they now had access to measurements from a region of space that could only be studied through remote observations from Earth-based telescopes. The crossing into interstellar space marked the beginning of Voyager 1's most scientifically valuable phase, even though the spacecraft was operating with 1970s technology that had already exceeded its design lifetime by decades. Every day of continued operation provided unprecedented data about conditions in the local interstellar neighborhood that surrounded our solar system. As the years passed and Voyager 1 continued racing deeper into this uncharted territory, the distances involved would soon reach scales that challenged human comprehension and created unprecedented technical obstacles for mission controllers. The 2025 Distance Milestone. As of February 2025, Voyager 1 has reached a staggering distance of 24,475,900,000 kilometers from Earth, positioning itself 167.34 astronomical units away from our home planet. This distance means the spacecraft has traveled over 162 times the Earth-Sun distance, venturing into a region of space where no human technology has ever operated before. Light itself, traveling at 300,000 kilometers per second, requires 22 hours, 35 minutes, and 9.8 seconds to make the one-way trip between Voyager 1 and Earth. The spacecraft continues extending this record daily, adding approximately 523 million kilometers to its journey each year as it races deeper into interstellar space. Every single day that passes, Voyager 1 extends its record as the most distant human-made object ever created, covering roughly 1.4 million kilometers in its relentless journey into the void. The spacecraft travels through interstellar space at a velocity of 61,000 kilometers per hour, moving at speeds that would carry it around Earth's equator in less than 2 hours. At this incredible velocity, Voyager 1 advances 3.57 astronomical units farther from the Sun each year, yet the vastness of space means that neighboring star systems remain tens of thousands of years away, even at this remarkable pace. The communication delays created by this extreme distance have transformed every interaction with Voyager 1 into a carefully orchestrated exercise in patience and precision. When mission controllers at NASA's Jet Propulsion Laboratory send a command to the spacecraft, they must wait over 22 hours to confirm that their instructions were received and executed properly. This delay means that troubleshooting any problems becomes an incredibly slow process where each diagnostic step takes nearly 2 full days to complete. Engineers cannot simply flip a switch or restart a system like they might with satellites in Earth orbit. The mathematical precision required to maintain contact with Voyager 1 at such distances pushes the boundaries of human technological capability. NASA's Deep Space Network must account for the spacecraft's position with accuracy measured in arcseconds, which represents angles smaller than the width of a human hair viewed from 100 yards away. The radio signals sent to and from Voyager 1 must be aimed with extraordinary precision, because even the slightest error in pointing direction would cause the transmission to miss the spacecraft entirely and disappear into the cosmos. Ground controllers track Voyager 1's position using a combination of radio ranging measurements and Doppler shift analysis that can detect velocity changes as small as a fraction of a millimeter per second. The spacecraft's trajectory must be calculated accounting for gravitational influences from the Sun, planets, and even large asteroids that can slightly alter its path over time. These calculations require supercomputers to process the complex orbital mechanics involved in predicting where Voyager 1 will be located when signals finally reach its position. The Deep Space Network relies on massive radio dishes to communicate with Voyager 1, but only one antenna on Earth possesses enough signal power to send commands to the distant spacecraft. Deep Space Station 43 in Canberra, Australia, operates the sole 70-meter antenna capable of transmitting instructions across the 24.5 billion kilometer gap to Voyager 1. This single point of failure creates a critical vulnerability in maintaining contact with humanity's most distant explorer, especially when the antenna requires maintenance or upgrades that temporarily sever the communication link. Signal strength becomes another major challenge at Voyager 1's current distance, because radio waves spread out over increasingly large areas as they travel through space. The spacecraft's transmitter produces only 23 watts of power, roughly equivalent to a refrigerator light bulb. Yet this faint signal must travel across interstellar distances where it becomes billions of times weaker by the time it reaches Earth. The Deep Space Network's sensitive receivers can detect signals so weak that they carry less energy than a snowflake hitting the ground. Voyager 1's current position represents the absolute edge of human technological reach, operating in a region of space where no backup systems or rescue missions could ever provide assistance. The spacecraft functions completely autonomously for days at a time between communication sessions, relying on computer systems built with 1970s technology to make critical decisions about power management, antenna pointing, and scientific observations. These ancient computers must continue operating flawlessly in an environment where cosmic radiation and extreme temperatures pose constant threats to electronic systems. The extreme distance complicates understanding any unusual behavior because traditional troubleshooting methods become nearly impossible to implement. When engineers detect irregularities in Voyager 1 systems, they cannot simply run quick diagnostic tests or request immediate status updates like they would with closer spacecraft. Every attempt to gather additional information requires a minimum of 45 hours to send a command and receive a response, turning simple diagnostics into multi-day investigations.